Hi, I'm Deepak. I'm with Liquid Brain, and I'm here to talk about massively parallel liquid cooling for AI supercomputing. Here's an outline of what we're going to talk about. So there's thermal plateau, and Moore's law is ending, as you probably know. Why liquid? And then the systems engineering that has to make this happen. The solution, which is microchannels, which we'll talk about quite a bit, and the future. So you've probably seen curves like this before. This is 40 years of Moore's law. The yellow dots are transistors in thousands increasing on a log scale, which is quite amazing. But the frequency in the green has plateaued over the last decade, and the number of logical cores has increased in the black on the bottom over the last decade. But the reason is thermal. Thermal has not improved over the last decade, and you're at about 200 watts per CPU over the last decade, and this is really the problem. So you have an exponential curve that's plateauing to ending right now. But while that's happening, there's a new exponential, and this is AI, and it's still in its infancy, but this is from OpenAI, and over the last 7 years, the complexity of AI models has increased by 300,000 times. So we've got a new super exponential here, and we have another exponential we just talked about that is plateauing, so we've got a bit of a problem. So how do we solve that? And liquid cooling can be one of the pieces to that problem. So why liquid? Liquid is 4,000 times more efficient than air at removing heat. It allows over 300 watts per centimeter square heat flux, and we'll get into some of the bigger numbers that can be even higher than that. And it allows new architectures for future growth. So, but to really make this happen, there's so many engineering issues that have to be solved in parallel simultaneously. So let's think about what has to happen. And these are just 9 of some of the issues, and we're going to come back to this again. So one is choice of materials, the thermal expansion of the materials, the temperature uniformity across the chip, fluid pressure drop, liquid flow rates, thermal resistance of the materials, parallelism so that you don't have single points of failure, large areas to enable new architectures, and the types of coolants. So let me show you something that we've done, which is the Liquid Brain Solution, which is a microchannel plate. What you're looking at in the picture there is a 12 by 12 centimeter ceramic insulating plate with tens of thousands of 3D microchannels. So this is massively parallel, and this plate is only 1 millimeter thick. So this is, maybe a small stack of paper. But with microchannels, the idea is very simple. What you're trying to do is increase the surface area, which is where the heat is going to leave, and while maintaining a reasonable amount of flow and pressure drop. So you want to keep basically taking a large pipe and instead replacing it with an array of small pipes. And this is well understood, but to fabricate this in the right materials, in the right ways to remove heat is a unique challenge. So what we've done is we've taken that microchannel we just showed in the past picture, and this is an array of chips on top of it. So the microchannel is now the PCB. It's everything. So that's one of the key things about having an insulating materials. You can now do multiple functions in the same material. So there's a finished PCB. There's 36 chips. This was particularly made for high-flux solar testing applications. The blue is the dielectric insulator. The black is the chips. It's been tested to 4 kilowatts thermal load, and that was purely a test commit limitation, and it can go much higher than that. Heat fluxes of 250 watts per centimeter square. It's capable of 10 kilowatts. So just to give you an idea of the area of this is the area of the size of your hand that can do 10 kilowatts of heat load while maintaining the chip temperature at 85 C or less. And this has been built and tested in real-world conditions. So the dish that you see there, it's been tested in outdoor solar conditions. This cooling system is at the focal point of that dish. It's a combined heat and power system. So the other key thing that we'll get into in a second is that this allows you to recover the waste heat at a very high efficiency, along with removing heat from the heat source. In this case, it was also generating photoelectric power. It was tested at the National Renewable Energy Lab in the US under high flux conditions also. And as we think about how we're going to decarbonize data centers, and a lot has been done, but there's much more to be done, and reusing the waste heat for other applications is another thing that is of great interest. So now let's talk about the systems engineering again. So we've simultaneously met all of these requirements that you see here. So let me discuss that a bit. The choice of materials, ceramic here, which is an insulator, and inert, which also means that the other parts of the system can be better. Thermal expansion, it's CT matched to the chip, which allows, again, an improvement in how you attach the chips to the surface, and we can talk about that later. Temperature uniformity, it's massively parallel, so that we've modeled this in great detail to show that the temperature distribution across the chip is uniform. Fluid pressure drop, it's only a few psi. Liquid flow rates that are just about tap water flow rates, so very low flow rates. Thermal resistance is extremely low. It's parallel with thousands of channels that I talked about. It's large area, 12 by 12 centimeters, 14,000 square millimeters, and it can be made even larger, up to 12 by 12 inches, actually, which is a full wafer size. And the coolant type, you can use water and glycol and the standard things that you're familiar with in liquid cooling. So here's a heat flux comparison. So an Intel Xeon 8168, it's a 205 watt TDP. It's about a 7 centimeter square die area, which is about a heat flux of 30 watts per centimeter square. Just looking at the OCP meeting from 6 months ago, that server was operating at 85 C, and one of the papers was presented with a 50-degree delta T with air cooling. With standard liquid cooling, it was a 27-degree delta T. With our microchannel system, which is 5x better than standard liquid cooling, it would be about a 5 C temperature rise. So you put that another way, if you had a 55 delta T budget, we can operate at 300 watts per centimeter squared compared to 60 watts per centimeter squared for regular liquid cooling. So this enables a huge number of new applications. So just in relative thermal performance, air, if you think about it as 1x in the red, standard liquid cooling is about a 2x improvement over that in the yellow. And the green, the first green line there next to it is our improvement, which is 5x over regular liquid cooling, so that's 10x better than air. And then another, with the next generation, another 2x improvement over that, which is 20x better than air, 10x better than regular liquid cooling. So let's talk about the future. I mean, there's this parallel array application allows a great deal of new opportunity. You've probably seen this picture from Cerebras, which is just announced last month in terms of very large scale wafer scale chips effectively. This had 1.2 trillion transistors, 46,000 millimeter square of area. This is actually liquid cooled, and it has 15 kilowatts of heat load, but that average flux is only 32 watts per centimeter square. And remember, the Xeon is also about that same amount. If you compare that to the NVIDIA, which they also have next to it, which is 21 billion transistors, 8 centimeter square roughly area, and a TDP of about 250 to 300 watts. And that gives you an average flux 36 watts per centimeter square. So in all of these systems, you're still at an average flux around 30 some odd watts a centimeter square, and we're at roughly 10 times that. We can get up to 250, 300 watts per centimeter square. So you have this opportunity now to build large-scale systems. If you think about the large array that I showed you before, with heterogeneous integration of different chips that have been optimized for their own specific functionality, as opposed to being dedicated to a wafer scale integration where maybe there's a lot of engineering challenges. And in particular, I think this is optimized for large scale matrix multiplications. And as you heard yesterday, matrix multiplications are not the only thing that you want to do. So having the ability to do lots of different things is a good thing. And where are we going with this? There's still the opportunity. I mean, Silicon Valley in general is now, and most companies are now thinking about what does artificial general intelligence look like, and which is human brain-like functionality. Well, we're still at the point where, if you think about this curve, it's a computational speed on the horizontal axis and memory on the vertical axis, one way to look at it. There's still lots of unknowns in all of this, but we're still about 100,000 times away from a human brain type capability, which is shown in the area in the triangle where the red arrow is. So there's still a tremendous room for new technologies and new solutions that we're going to have to solve. So when you think about the plumbing of the future, we have to think about how compute, interconnects, power, and thermal are all integrated and designed in parallel, with all of them being kind of equal partners in the solution. Whereas right now, some of these things, especially the thermal, is somewhat of an afterthought. But we have to integrate them all, and this is just one way of thinking about how we should do that in the design process. And finally, we can be inspired by biology too. If we're really going to get to that brain-like functionality, then the picture on the right there, neurons with synapses and blood vessels, you really can't think of the microchannel as the capillary blood vessel of the compute world. And there really are some very interesting synergies between thinking about the parallelism, the branching of information, energy, and liquid in the biological world and what we can do in the compute world. So the path forward, we have new thermal technology for single chips. It can be up to 300 watts per centimeter squared, and actually even higher in the future. You can think about large arrays of chips, as I already showed you in one of the pictures, where you could think about dozens of chips on a single substrate, 10 kilowatts of heat load in the size of your hand while maintaining the junction temperature of the chips. So, in the future, can we think about 1,000 GPUs or AI chips in a cubic foot? And this is really potentially possible. That cooling plate that I talked about is only 1 millimeter thick. You could think about half-inch pitch dimensions, and all of that fitting under your desk and having 5 to 10 million cores. So this is just something that we, as a community, can start to think about what the next generation can be. And then the next 100,000x, can we be inspired by biology and combining all of these aspects of compute, interconnects, and architecture in new ways? So maybe we'll have open brain next. So thank you.